Hello everyone, I'm Professor Mangesh Joshi. Today we will see the shortest path algorithms. So how can we find the shortest route between 2 points on a roadmap? So basically this algorithm will answer this question. Suppose you're having the graph. So at one point you have your market, and these are the several market available at different geographical locations, and you have factory. So you can find out the shortest route between the 2 points on a roadmap. Okay. So model the problem as a graph problem. So we will be modeling it as a graphical problem. So roadmap is a weighted graph where vertices are nothing but cities, edges are nothing but road segments between cities, and edge weights are nothing but road distances or traveling costs. So your goal is to find out the shortest path between two vertices. So there will be one originating point and there will be some destination point. So you will be finding out the shortest path. The same application is given. That is, you have to start from here, and suppose you want to, this is your destination and this is your original point. So this graph basically will be a directional graph. In minimum spanning tree algorithms, you are having a directionless graph, but in this case you will be given with some directions, right? So there are many algorithms which deals with shortest path method. So popular algorithms are Dijkstra algorithm and Bellmans force algorithm. So let us see both the algorithms one by one. So let us take Dijkstra algorithm. So this is the sample case given to you where originating point is A and destination point is F. And there are multiple paths which you can go. That is, for example, there is one path that is A, B, D and F. There is one more path that is A, C, E, F. There is one more path that is A, B, C, E, F. There is one more path A, C, E, D, F. So there will be many more paths, right? So one of the paths which may give you the optimal solution having the shortest distance or shortest cost of transportation, right? So in this case there are vertices. Total number of vertices are 6, right? So you are having this much paths. So imagine a problem where you have m vertices. So it will become more complex if the number of vertices and number of paths are increasing. Okay, so that's why you need a computer algorithm to solve it quickly, and it will be a beyond scope of manual calculations. So that's why this algorithm. So let us understand how this algorithm works. So as set 0, again this is a greedy type of algorithm in which you have to solve in stages. Okay. Stage by stage you will get optimal solutions. You have to update the solution obtained in the previous stage with the new value. Okay, so at stage 0, so it will start with 0, right? Because the originating station will have the cost of transportation as 0, and we will put all the other cost as unknown, which is infinity at stage 0. Then we will gradually update all this costs based on the value. So at stage 0 you can see that the table at A it is 0 and remaining I have put the infinity sign. Then at stage 1, so we will list down the paths originating from edge vertex A. So you can see that there is A to B and A to C. So we will select the smaller or shortest path, that is A to B. So you can see that in the table A to B is fixed, that is 2, and A to C is 4, that is C is 4. So we have updated B to C, right? So instead of infinity now it is 2. Here instead of infinity now it is 4, but remaining all are infinities, right? So in stage 3, so now since we have phrased this, so we have B to C and B to 7. Okay, now in this case, so what was the previously, it was 2 and it was infinity. It was not infinity, it was 4, right? So in this case it is 2, it was 4. Now we have updated it, that is 2 plus 1, that is it will now become 3. So you can see that the value of C in the table is 3. Similarly from B, as soon as I'm freezing this A to B, the new path is there, that is B to D, having weight of 7. So this infinity will be replaced with 7. 2 plus 7, it is nothing but 9, right? So you can see in the D column it is written over 9. So from the available options 3, 9, infinity, infinity, this is still infinity and this is still infinity. 3, 9, infinity, infinity, we have to select the least one, so which is 3. So we will now freeze path A, B and C. In the next iteration we have seen that now this BC is fixed, so new path emerging from C will now get updated. So here it was infinity earlier, here it was 9 earlier, here it was infinity earlier. So and here it was 3. So 3 plus 3, so it will be now updated to 6, right? So similarly you can see 9, 6 and infinity. So since 6 is lesser, we will now freeze the path C to E. Okay. Now we have 3 over here, 6 over here, 9 over here and infinity over here. So 6 plus 2. Now since CE is fixed, 6 plus 2 is 8 and hence we will update this 9 with 8, right? So from 8 and infinity, the least you have to select, which is 8. The last iteration, you can see that this was 8, this was infinity, this was 6. So once you have phrased this, there is, okay, so this was 6 plus 5, 11 earlier, not infinity, because since we have phase CE, we have to take the path emerging from EF. So in the previous stage, it was become infinite. 6 plus 5 is 11. Now since in the stage 6 we have phrased 9, so not 9, this is in the previous stage we have calculated it as 8, but we have not updated this. So this was 6 plus 5, 11, right? So in the next stage, last stage, it was 8, 11, right? And now we will update this 8 plus 1 is 11, because 8 plus 1 is 9. So since it is less than 11, we will update it with 9. And finally, you will get the least cost, that is 9, from the path, shortest path, A to B, B to C, C to E, E to D, and D to F. Okay. So in this way, we have calculated the shortest path and shortest cost. Let us move on to second algorithm, that is Bellman's Ford algorithm. So once again, we will take the same problem. So the Bellman's Ford algorithm works by overestimating the length of the path from the starting vertex to all other vertices. Then it iteratively relaxes those estimates by finding new paths that are shorter than the previously overestimated paths. So what is the procedure for Bellman's Ford algorithm is, first you have to list down all the edges. Then edge relaxation criteria is, if the distance of u plus cost associated with u and v is less than distance of the destination. For example, if this is u and this is v, so how is the condition? If distance of u, that is, suppose initially it is 0, so it is if 0 plus cost associated with u and v is 2, so 2 is less than the distance of b, so initially it is infinity, so it is less than infinity, yes, so this condition is satisfied, and hence you will update the distance of v. So how will you update? It is nothing but du of v, that is 0, plus cost of uv, it is 2, so it is 2. So this infinity will be cancelled and it will be updated to 2, similar to Dijkstra algorithm, right? And number of iterations to be performed is number of vertices minus 1. So there is a limitation in number of iterations, that is number of available vertices, that is 5, minus 1, that is not number of available vertices are 6, minus 1, that will comes out to be 5. Let us understand the working of this Bellman's Ford algorithm. So if we take this problem, so I have listed down all the edges AB, AC, BC, CE, BD, ED, DF, and EF, and number of iterations should be 5. 6 minus 1, 5. After doing this, let us start iteration 1. So we will go by step, that is AB. So 0 plus 2, initially everything will be infinity. So first stage AB, 0 plus 2, yes, it is less than infinity, so it is 2. Then A to C, 0 plus 4, yes, it is less than infinity, so this will be 4. Next is BC, so 2 plus 1 is 3 and it is less than 4, and hence it will be 3. Just focus on the direction of the arrows. Okay. So since the arrow is emerging from B and it is destination is C, hence we have gone like this. Okay, 2 plus 1, 3. And since it is less than 4, we have updated it to be 3. This is iteration 1 only. Then next is CE. 3 plus 3 is 6, which is less than infinity, and hence this will be updated to 6. Then BD. 2 plus 7 is 9, then ED, 6 plus 2 is 8, and hence it is less than 9, we will update it with 8. Then DF, 8 plus 1, yes, it is less than infinity, hence it is 8 plus 1 is 9. EF, 6 plus 5 is 11, so 11 is greater than 9, and hence we will not update the solution. So the final path is 9. Okay, now this was the iteration 1. So you have obtained this answer in only one iteration. Okay, in the second iteration again we have to go by this, that is AB, AC, BC, CE. So let us check once again. Suppose iteration 2. So it will basically perform 5 iteration compulsorily in a computer program. Even if you are getting the solution, optimal solution in the first iteration itself, but still the computer will perform all the iterations. So iteration 2, AB 0 plus 2, it is 2, hence no update. AC 0 plus 4, it is greater than 3, no update. Then BC 2 plus 3, it is 3, equal, so no update. CE 3 plus 3 is 6, no update. PD 2 plus 7 9, which is greater than 8, so do not update. Then ED 6 plus 2 is 8, which is you already written it. Then DF 8 plus 1 is 9, you already written it. And EF 6 plus 5 is 11, which is greater than 9, hence I do not update. So in all the iterations you will getting the same answer. So computer will perform all the iterations and then you will give you the final answer as 9, right? So all these iterations are given over here, which I have just explained you. So what is the difference between the Dijkstra algorithm and Bellman's Ford algorithm? So Bellman-Ford's algorithm is a single source shortest path algorithm. So when you have a negative edge, again this both the algorithms are single source shortest path algorithms. So when you have a negative edge weight, then it can detect negative cycles in the graph. The only difference between the two algorithms is Bellman's Ford algorithm is also capable of handling negative weights, whereas Dijkstra algorithm can only handle positive values. Okay, so let us see one example with reference to the negative values. Okay, so this is one example. So we have total 1 2 3 4 5 6 vertices, and hence the number of iterations will be 5. So iteration 1, iteration 2, iteration 3, iteration 4, and iteration 5. Okay, so first iteration. So let us go with the first iteration. We have listed down all the paths: AB, AC, AD, BE, CE, DC, DF, EF, and BC. Okay, so again there is no meaning to the sequence. You can list down it randomly. CB and BC is same, AB and BA is same. Okay, so let us start the first iteration, that is first is AB. So A to B 0 plus 6, so infinity will be cancelled and 6 will be here. Similarly next AC 0 plus 4, 4 is written over here. AD 0 plus 5, 5 is written over here. Then BE 6 minus 1 is 5, right? Then CE 4 plus 3 is 7, which is greater than 5, so do not consider. Then DC 5 minus 2 is 3, which is less than 4, and hence cancel this, new value is 3. Then DF 5 minus 1, so cancel this infinity, the new value is 4. EF 5 plus 3, which is 8, which is greater than 4. Hence, do not consider this value. Then CB is 4 minus 2, means 3 minus 2, it is 1. So since it is less than 6, consider this value. So this was the iteration 1, right? Again, start with iteration 2, the same procedure. That is A to B, 0 plus 6. It is, okay, I will highlight these values, what we have obtained after one iteration. So this was the value which I obtained after first iteration. This was the value. This 5 was the value after first iteration. This 5 obtained after the first iteration. Then in this case, this 4 was obtained in the first iteration. Okay. So iteration number second. AB 0 plus 6. It is greater than 1 and hence do not consider. Then AC 0 plus 4, which is greater than 3, so do not consider. AD 0 plus 5, it is already the same. BE, B to E, that is 1 minus 1. Now it becomes 0. Okay. Now CE 3 plus 3 6, which is greater than 0, hence do not consider. DC 5 minus 2, again it's the same value, which is 3. Then DF 5 minus 1, 4, again it is the same value. Then EF 0 plus 3 is now will be updated with 3. So this BC is now it has updated to 3. So this was iteration 2. So few more values got updated in iteration 2. Now let us check once again with the iteration 3. Computer will perform all the 5 iterations. Now let us check all the values. So we have already obtained this 1, 3, 5, 0 and finally 3. Okay. So even if you perform the third iteration, fourth iteration and fifth iteration, you will get all the value as it is. Your no value will be updated in any of the iterations further. So you obtain the optimal value at the third iteration in the second iteration using Bellmans Ford algorithm. I hope you have understood this. If you have any queries, you can ask. So thank you for watching this video lecture. You can send your queries or requests to untwistedlearning@gmail.com. Thank you so much and have a nice day.